LeChatelier's principle. Spelled LeChatelier's, pronounced LeChatelier, because it's French. LeChatelier's principle states that when a system at equilibrium is disturbed, so that it's no longer at equilibrium, the system responds to restore that equilibrium. So let's dig into this. What does it mean for a system to be disturbed? So what does it mean to disturb an equilibrium? Well, you could increase the concentration of something by adding it to the reaction vessel. On the other hand, you could remove something from the reaction vessel. On the other hand, you could raise the temperature, or you could lower the temperature, or you could get really fancy and change the volume of the reaction vessel. Doing any or all of these things will affect the equilibrium. It will take you away from equilibrium. What does the system do? It restores equilibrium. How do we see this? Well, we can see it by looking at the equilibrium constant expression. So let's consider a generic endothermic reaction. A moles of A plus B moles of B plus heat yields C moles of C plus D moles of D. Heat is on the reactant side because the reaction is endothermic. At equilibrium, we have our equilibrium expression that says KEQ equals the concentrations of the products raised to their coefficients over the concentrations of the reactants raised to their coefficients. So, let's say we add some product C to the mix. That means that our numerator is too big. And so the reaction shifts to the left. So, adding C, this is what we did to disturb the equilibrium. Shifting left is the response. Okay, so don't get those two things confused. A lot of people do. You can think of it as we took C and we put it into this side of the equation, and that pushes everything to the left. On the other hand, what if we removed some of the product? That makes our numerator too small. And so the response is going to be to shift to the right. You can think of that as a pull. So I'm pulling C out, and that pulls the whole equilibrium to the right. So again, removing the product, that's disturbing the equilibrium. That's what we do. And the response is what the equilibrium does. It shifts to the right. We could also add stuff to the reactant side, which would push to the right, or we could remove stuff from the reactant side, which would pull to the left. And since you can consider heat as a reactant, well, what if we raise the temperature? In the push-pull model, raising temperature is like adding heat, which pushes the reaction to the right. So the response is to shift right. What does that mean in terms of concentrations? That means the concentrations of reactants go down, right? So A and B go down. At the same time, the concentrations of products, C and D, go up. So here's an exercise. We have an exothermic reaction. A moles of A plus B moles of B yields C moles of C plus heat. And it's at equilibrium at 25 degrees Celsius. So then you put the reaction vessel in an ice water bath. What happens? In other words, what happens to the concentration of everything? Pause the video and work. Then unpause to see my answer. So here's how I think about this. We put it in an ice water bath. That pulls heat out, which pulls the whole reaction to the right. So what does that mean for concentrations? That means the concentration of A and the concentration of B go down, and it means the concentration of C goes up. In other words, more reactants are made into products. Did you get the same answer? Excellent.